Hello everyone, welcome to the fifth lecture of AAE 301. In today's lecture, we will be talking about discrete Fourier transform. Okay, let's start with an overview of the lecture today. So the discrete Fourier transform, or DFT, is a method that can be used to compute a Fourier series approximation for a function f of t in the Lebesgue space by taking samples of the function. And this method is particularly useful when the function f of t is unknown. Here on the left is a plot showing the number of sunspots each year. And say now we want to obtain a Fourier series approximation for this function. What we can do is we can take samples of this function, and then we can run DFT on the samples to obtain the Fourier coefficients of this function. And once we have the Fourier coefficients, we can then use it to compute a Fourier series approximation of this function. So this is the overview of what you will be learning today. And now let's move on to the details. First, let's consider a function f of t in the Lebesgue space L squared with the interval from 0 to tau. Here, the Fourier series representation for this function is given by the summation of ak times e to the negative I k omega t, and k is from negative infinity to positive infinity. And its Fourier series approximation is given by p of t, which is equal to the summation of ak times e to the negative I k omega t, and here k is from negative m to n. And to help you better understand, here I have a graph showing a triangular function in the Lebesgue space L squared with the interval from 0 to 2, and its Fourier series approximation with n and m both equal to 2. Now I have a question for you. So suppose you can take new uniformly distributed samples along the interval from 0 to tau of p of t. That is, if you can measure the value of p of t at the equally spaced points tj, and here tj is equal to j tau over nu, and j is an integer index from 0 all the way to nu minus 1. And the question is, how can you solve for the Fourier coefficients ak given these samples? So again, to help you better understand the question, let's look at the example that we have seen just now. So the red line here again is the Fourier series approximation for the triangle function. And now we take 5 equally spaced samples of the function. So the first sample is right here, the second sample, the third sample, the fourth, and the fifth. And now, given these samples, we are asked to estimate the Fourier coefficients associated with this approximation function. And the answer to this question is this can actually be done by DFT. And now let's see how it works. First, let's recall the approximation function p of t is given by the summation of ak times e to the negative I k omega t, and k is from negative m to n. And recall that omega naught is given by 2 pi over tau. So we substitute this into the expression, and we will get this expression on the right. Now, this summation here can be broken down into 3 parts, a naught, and the summation for the negative case, and the summation for the positive case. And we want to get rid of the summation with the negative case. So here we do a sign flip to make the summation to be from positive 1 all the way to n. And that is also why here we will have a negative k, and the power of the exponential function will be positive as well. And now let's look at the value of the approximation function at each sample point tj. And tj here is equal to j tau over nu. So to obtain the value of the approximation function at each sample point, we simply substitute t equals to tj into the expression of p of t. And this will give us a naught plus the summation of a negative k times e to the I k 2 pi over tau times tj, and k is from 1 to m, plus the summation of ak times e to the negative I k times 2 pi over tau times tj, and k is from 1 to n. And now we substitute Tj equals to j tau over nu into the expression, and we will get this expression shown here. And you can see that here we will have tau in the denominator and also a tau in the numerator. And because of this, we can cancel them out. And in the end, we will be left with 2 pi j over nu and also 2 pi j over nu over here. And now you can see that e to the ik times 2 pi j over nu can actually be seen as the kth power of e to the I times 2 pi j over nu. And similarly, e to the negative ik times 2 pi j over nu can be seen as the kth power of e to the negative I times 2 pi j over nu. And now if we let lambda j to be equal to e to the negative I times 2 pi j over nu, then you will see that this term right here is actually just lambda negative j. So in the end, we see that P of Tj will equal to A naught plus the summation of A negative k times the kth power of lambda negative j, and k is from 1 to m, plus the summation of AK times the kth power of lambda j, and k is from 1 to n. Now, if we stack the values of the samples from j equals to 0, 1, 2, all the way to nu minus 1 together in a vector, then the result can actually be expressed in a matrix vector form as follows. So here on the left, we have all the samples, pt naught, pt1, all the way to pt nu minus 1. And on the right, we will have all the coefficients that we would like to estimate. So A naught, A1, A2, all the way to A negative 2, A negative 1. And the matrix that connects the samples and the coefficients is what we call the discrete Fourier transform matrix. And this matrix is of size nu times n plus m plus 1. And just as a reminder, nu here is the number of samples, and n plus m plus 1 is the number of Fourier coefficients that we would like to estimate. Now, when the number of samples nu is equal to the number of Fourier coefficients, then a discrete Fourier transform matrix will become a nu by nu square matrix, which is given by the expression shown here. In the following discussion, we will call this nu by nu DFT matrix F nu, and the vector that contains all the samples P, and the vector that contains all the Fourier coefficients A. Then we see that P will equals to F nu times A. And because F nu is a square matrix that is invertible, this implies that the coefficients can be solved by multiplying the inverse of the square matrix F nu by P. Let's go back to the example that we have seen just now. So for this example, there are in total 5 Fourier coefficients that needed to be estimated: A negative 2, A negative 1, A naught, A1, and A2. And the analytical value of these coefficients are given by 0, negative 0.4053i, 0, 0.4053i, 0, and we can also compute the values of these coefficients numerically through DFT, and you can see that in the end, you will get something very, very similar to the analytical values. Now, before I end this section, let's go through some remarks together. First of all, given equally spaced samples of the Fourier series approximation P of t for the function f of t, one can solve for the Fourier coefficients corresponding to P of t using DFT. Second, if A is a vector in C nu and P equals to F nu times A, then we say P is the discrete Fourier transform of A, and A is the inverse discrete Fourier transform of P. The last one is the square matrix F nu is invertible, and its inverse is given by the complex conjugate transpose of F of nu over nu. And because F nu is invertible, this also implies that A and P can uniquely determine each other. Now let's take a look at the fast Fourier transform, or FFT. So basically, FFT is an efficient algorithm for calculating the DFT. And to see how efficient it can be, let's first recall that F nu is a nu by nu matrix. And in general, it takes nu squared operations to compute the vector P equals to F nu times A, given the coefficient vector A. However, if nu is a power of 2, then one can exploit the special structure of F nu to construct an algorithm called FFT to compute the vector P in nu times log nu operations. And for example, let's say nu is equal to 10 to the power of 6, then if you compute the vector P according to the definition of DFT, then it's going to take nu times nu operations. So that's going to be 10 to the power of 12 operations. And if you compute the vector P using FFT, then it's going to take nu times log nu operations, which equal to 6 times 10 to the power of 6 operations. And you can see that this is much lower than 10 to the power of 12. And this is going to be a speed of about 1600 times. And to put it into numbers, it's basically going to be 1 second computation time versus 46.3 hours computation time. And if you want to know more about FFT, here are 2 papers that I will suggest you to read. And these papers are very short. Each of them only has 2 to 3 pages. And the first paper is a paper in 1965, which is called An Algorithm for the Machine Calculation of Complex Numbers. And the second paper is a paper in 1985, which is called Gauss and the History of the Fast Fourier Transform. Okay, now let's talk about the relationship between FFT and the Fourier series. First, let's recall what FFT does. Basically, FFT computes the Fourier coefficients associated with the approximation function PT. And here, the number of coefficients is equal to nu. And we know that as the number of coefficients increases, the approximation function is going to approach the original function f of t. So here, let's look at the example that we have talked about. And we see that when the number of coefficients is equal to 5, we will obtain this red line as an approximation for the triangle function in the blue line. And as we increase the number of coefficients, we see that the approximation better approximates the original triangle function. So we know that when the number of coefficients is large, the samples that we take on the approximation function can actually be approximated by the samples taken on the original function. And now if we run inverse fast Fourier transform on these samples, we can get a set of coefficients Ck. And this set of coefficients will be a very good approximation for the Fourier coefficients associated with the approximation function. Now let's take a look at an example. In this example, we will apply fast Fourier transform to construct an approximation for a function f of t. So first, let's consider a function f of t in the Lebesgue space L squared with the interval from 0 to 2 pi. And this function is given by cosine of 2t plus e to the power of sine of 6t. And now we would like to obtain approximation for this function pt, which is given by summation of ak times e to the I k omega t, and k is from negative 20 to 20. And you can see that in order to compute this approximation, we would have to determine the Fourier coefficients ak. But with this function that we have here, it is very difficult to compute ak by the definition, which is the inner product of f and e to the negative ik omega t. So instead of computing ak by following the definition. Here we are going to compute AK numerically through FFT. And here are three steps we can follow to compute the coefficients. So first, we are going to take nu equals to 4096 equally spaced samples of the function f of t. And then we will run inverse FFT on the samples to obtain the set of coefficients CK. And as we have talked about just now, this set of coefficients CK is going to be a good approximation for the Fourier coefficients associated with the Fourier approximation. So that's why we can then use this set of coefficients CK to construct a Fourier series approximation PT for the function f of t. And now I'm going to show you how you can do this on MATLAB. So first of all, we know that the function is in the Lebesgue space L squared with interval from 0 to 2 pi. And we are going to take 4096 samples on this interval. So here we have t equals to length space 0 and 2 pi and 2 to the power of nu, which is equal to 4096 in this case. And now we're going to measure the values of f at these sample points. So here we have cosine of 2t plus exponential to the power of sine of 60. And once we have obtained the samples, we are going to run inverse fast Fourier transform on the samples to obtain the coefficients C. And once we have obtained the coefficients, we can then construct a Fourier series approximation using those coefficients. So here the approximation is going to be from k equals to -20 all the way to 20. So in total, we will have 41 coefficients. And now I'm going to show you what we get in the end. So here there are two lines in this plot, the blue line and the red dashed line. So the blue line will be the original function, and the red dashed line will be the approximation for the function. And you can see in this plot, we basically have obtained a very good approximation PT for the original function ft. Now let's continue. Now let's look at how we can compute the inner product in the Lebesgue space with the interval from 0 to tau using FFT. So first, let's consider two functions f and g in the Lebesgue space. And for these two functions, their Fourier series of representation are given by the following. So f of t is equal to the summation of ak times e to the negative I k omega t, and k is from negative infinity to positive infinity. G of t is equal to the summation of bk times e to the negative I k omega t, and k is from negative infinity to infinity. Now recall that a naught is given by 1 over tau times the integration of f of t from 0 to tau with respect to t, and the total power of f is equal to the summation of the square of the absolute value of ak, and k is from negative infinity to positive infinity. And this is by the Parseval equality. And last, we have the inner product of f and g, and this is going to be equal to the summation of ak times the complex conjugate of bk, and k is from negative infinity to positive infinity. And we see that to compute these values, we would have to obtain the coefficients ak and bk. And because we also know that FFT can be used to obtain the coefficients ak and bk, so this means that we can obtain these values using FFT. Now let's take a look at an example. So in this example, we will be looking at two functions, f of t and g of t in the Lebesgue space, L squared with the interval from 0 to 1. And in this case, f of t is equal to t and g of t is equal to t squared. And let's first compute these values analytically So here A naught is equal to 1/2, and the total power of F is equal to 1/3, and the inner product of F and G is equal to 1/4. And now let's see how we can compute these values numerically using FFT in MATLAB. So in this example, we are going to take 4,096 samples on the interval from 0 to 1. So that's why here we have t equals to lin space 0, 1, and 4,096. And here f is given by t and g is given by t squared. And the next thing we are gonna do is we're gonna run inverse fast Fourier transform on these samples and to obtain the coefficients A and B. And after we have obtained the coefficients, we can then determine the values that we are interested in. So basically, A naught is going to be the first element in the vector A, and the total power of F is going to be the sum of the squared of the absolute value of AK. And the inner product of F and G will be the summation of AK times the complex conjugate of BK. And the summation is from negative infinity to positive infinity. And now let's see what MATLAB gives us. So first, A naught will be a 0.5, which is equal to 1/2. So these values match each other. And the second thing is going to be the total power of F. And we see that it's going to be 0.3334. And basically that's equal to 1/3. So these two values also match each other. And last, we are going to look at the inner product of F and G. And in the end, we have 0.2501 plus 0I. Basically, this is going to be 1/4. So again, we see that these two values match each other. So this is how you can compute the inner products in the Lebesgue space using the fast Fourier transform. Okay, now let's look at how we can perform sinusoidal estimation using FFT. And to give you more context of what this problem is about, let's look at this function g of t, which is a function in the Lebesgue space L squared with the interval from 0 to tau. And this function g of t is in the form of summation bm times e to the negative I theta m times 2 pi times t, and m is in the integer set m. Also here, bm and theta m are unknown amplitudes and frequencies to be estimated. So the sinusoidal estimation problem basically is to estimate the unknown frequencies and the unknown amplitudes by sampling the function g of t at new points in the interval from 0 to tau. Now, to solve this problem, what we can do is we can approximate the function g of t by its Fourier series approximation, f of t, which is in the form of summation ck times e to the negative I k over tau times 2 pi times t, and k here is in the integer set k. And as you can imagine, in order to obtain the coefficient ck, we can run inverse fast Fourier transform on the samples to obtain the coefficients. And we know that if the number of samples is large enough, then the amplitudes bm can be approximated by the coefficients ck, and the frequencies theta m can be approximated by k over tau. Now let's look at a numerical example. In this example, we will be looking at this sunspot peak period estimation problem. Basically, scientists are very interested in the activity of the sun, and they have observed the number of sunspots every year from the 1700 all the way to 2023. In this graph, you can see how the number of sunspots vary each year from the 1700 all the way to 2023. And you can also see that the number of sunspot peaks every few years. Now, the goal of this problem is to estimate the period of the peak. And as you can imagine, in order to solve this problem, we can run inverse fast Fourier transform on the samples to obtain the Fourier coefficients associated with this function. And here I'm not going to show you how to do that on MATLAB. Instead, I'm just going to show you the power spectrum associated with the function. Now, if you look at the power spectrum, you can see that this power spectrum can be divided into 3 different regions. The first region will be this A naught. The second region will be these sinusoidal components with lower frequencies. And the third region will be these sinusoidal components with higher frequencies. And you can see these 3 different regions in the plot as well. So the first region, which is this A naught, is basically going to be this purple constant line here that tells you the average power of the function GT. And the orange line and the green line here are the sinusoidal components associated with the lower frequencies. And the red line here are the sinusoidal components associated with higher frequencies. And these sinusoidal components are those associated with the peaks. Now, according to the sunspot plot, the sinusoidal component associated with the peaks is very easy to observe. And this implies that these components have high power. So now let's see which integer k will give us the highest power in this third region. And if you do this on MATLAB, you're going to see k equals to 29 and negative 29 are going to give you the highest power. And now that we know that this sinusoidal component is associated with k equals to 29, we can then estimate the frequency of the peak by k over tau. And tau in this case is going to be 2023 minus 1700 plus 1, which equals to 324. So in the end, we will have the frequency of the peak as 29 over 324, which is approximately 0.0895. And also we know that the period is basically just the reciprocal of the frequency. So the period is going to be 1 over 0.0895, and that's about 11.1724 years. And so in the end, we can conclude that the maximum sunspot activity occurs about every 11 years. Great. This is the end of the lecture today, and I hope to see you in the next one.